Croeso nôl, welcome back, year 11. This is lesson 4 from the Work and Energy booklet. At the end of lesson 3, we finished page 21, so we start in on page 22 today. So please turn on to that page and just put at the top of the page lesson 4 and the date. Before we start any activities, let's quickly look to see what the learning objectives are for today. So it's lesson 4, pages 22 to 28. And it's the remaining content of the booklet. There are some additional exam questions at the end, but this work here is what we're going to be covering during lesson 4, and it's all to do with vehicles and the physics of vehicles and how you can keep vehicles efficient and how you can keep people in the vehicles safe. Now, the first part then will be looking at how energy efficiency of vehicles can be improved by reducing aerodynamic losses, air resistance and rolling resistance, and be able to give examples of how to reduce losses, which include rolling resistance, stop-start systems and so on. And those are the pages we'll be doing. So before we make a start, on this first page, page 22, it's asking you to do a bit of prior learning, reflection time, reflect on what we've already learned. So just pause the video, and what I'd like you to do is draw lines between the blue box, the red box and the image. I've completed the first one because the motorbike has got motion and kinetic energy. So you complete the next two. Okay, that looks a bit messy, so I'll go through each one of those one by one. I've already done the motorbike. So that's this one here. The motorbike is moving, it's got kinetic energy. The elastic band has got elastic energy, and deformation means changing its shape. So that leaves us with the dandelion seed, it looks like to me. Not so obvious. It's got height because it's moving through the air. So we say at height it's got gravitational potential energy, so it's to do with its position, its height. When you've completed that, please turn over to page 23, and this is what it should look like. On the top it just says this version of the Wales team coach has a number of design features that are intended to increase the efficiency of the vehicle. Remember, efficiency means how much of the input energy is transferred to useful energy. In the case of a bus or a vehicle, the input energy is the fuel, the petrol or diesel, and the useful output energy is kinetic energy. What you need to do is use your handout sheet to label this bus, this coach. And I've done one there. So you get your handout, you cut out each box and you stick it on the appropriate part of the page and draw an arrow. So if we look at this first one that I've already snipped and stuck in, the bottom of the coach is closer to the ground and the wheels are more enclosed by the wheel arches. This also improves the the aerodynamics of the coach and reduces air resistance, improving the fuel economy, improving the efficiency. What you need to do now then is the same for the remaining boxes you see on the left hand side of the screen. So pause the video now and complete that activity. Okay, yours won't look exactly like this, but I just go through each one now quickly to see whether you have something similar. So the front top surface is raked at an angle. What they mean by that is, rather than go straight up, it comes at an angle just like that. That's to improve the efficiency and aerodynamics. Now, this one here, that could have gone anywhere really, because it's talking about the lightweight materials. This one about tyres, balance between good grip on the road but not too much grip, otherwise it makes the bus less efficient. This one I'd had on previously, that's the bottom of the coach. This one you could have put anywhere, but I've put it really as close as I could to the engine, because it's to do with the vehicle when it's idling in traffic, not to reduce the amount of energy loss. You might find vehicles these days that idling means standing still or waiting at traffic lights or in a traffic jam, so that rather than the engine continue to idle or tick over, perhaps is a more old-fashioned term, the engine switches off automatically, and then as soon as the user, or the driver I should say, presses the accelerator, then the engine starts up again. That just saves petrol. And the remaining one here, the edges of the outer surface of the coach are rounded, improving the aerodynamics. Tick those if you got them right. You might want to change where the arrow's pointing to after watching that. And then we'll move on to the next page, page 24. So this is how we improve vehicle safety. Pause the video and read through the first paragraph. Now you've read that, you follow this instruction here, which is to add the correct label to the following car safety diagrams. I'll do one of them. If we look at this, or these two here, well, the one on the right hand side is most obvious, because you can see here you've got airbags. So I'll take that label from the box above and I'll just write in airbags. And when I've done that, I'll put a line through it so I know that the other labels need to be used for the other photographs. Okay, again, pause the video and complete and cross off the different safety features as you go along. Okay, if you can compare yours to these answers, tick them right with a red pen if you got them right, or correct them if needed. First one, seatbelt. Oh, I think we all know there's your seatbelt. So that's preventing the driver or passenger being thrown forward during impact and colliding with the windscreen. Airbags. I suppose in everyday language we'd use the words cushion the blow. We look more into the science behind that, the understanding of cushion the blow in a moment. In essence, what we're trying to do is to reduce the force acting on the passenger, and we do that by increasing the time. Well, more of that later. When I say the time it takes for the passenger to go from travelling at a certain speed to becoming stationary. Front and rear crumple zones. They speak for themselves. They take the energy out of the collision, and again they increase the time it takes for that car to come to a standstill, and rather than the main part of the car crumpling, which obviously would be dangerous for the passengers and driver inside, the crumpling takes place in these crumple zones instead, keeping the main part of the car intact. Side impact bars, steel cage, so that goes together with the crumple zones, where you've got this rigidity in the passenger steel cage, but then you've got the crumple zones either side of it. Seatbelt pretensioners, and finally the steering column, which is this part here, collapses during impact. So just check you've got those answers. And Mr. Ruddy's put this photograph in, look, to show you what happens when you haven't got the steel cage here and those different safety features. So this car was probably certainly pre-1960s, probably 1950s even, and the driver and passengers there, of course, they would have been seriously injured, possible fatality. But with all these design features and car safety features put in place now, you can see that cars have become much safer. Let's look at the science behind it, the physics behind it. So if you're in a car that suddenly slows down, you keep moving forward until a force acts on you. That's Newton's first law. We've learnt about that, and that's shown in the box here. And that's Newton's first law. The force that changes your velocity could be the force between your head and the windscreen, or your chest and the steering wheel. So we want this force to be as small as possible. Remember Newton's second law here. It's reminding us here that the force is dependent on two things. The bigger the acceleration or deceleration, the bigger the force, and the bigger the mass, the bigger the force. So what we want to do is keep the size of this force as low as possible. We can't really change the mass of the driver, but what we can do is to reduce the acceleration. Quick recap on acceleration then. Acceleration is change in velocity over change in time. Now, the velocity, obviously the slower the car's moving, the less danger there is to the driver and passenger in the instance of an impact. But if we're not changing the speed, then what we're saying is this again, meaning that the time taken, the longer the time it takes to bring the car to a stationary position or to rest, the smaller the acceleration, and the smaller the acceleration, the smaller the force. Going back to this equation, so the smaller the acceleration, the smaller the force. and again, we use the words proportionality. So the smaller the acceleration, the smaller the force, meaning force is directly proportional to the acceleration. I'm going back up here. We can say the time is inversely proportional to the acceleration. If we put those two together, what's the relationship then between the force and the time? Well, the bigger the time it takes to make the passenger stop, the larger the time takes, the smaller the force on the passenger or the driver. So the relationship there is inversely proportional. So what we're trying to do then is cushion the blow, increase the time of impact. And you can see, if we look at these photos underneath, first one, a bullet stopped by a bulletproof glass, an example of huge descent. I'll highlight the important bits here. So, huge deceleration, large force. You've got this gentleman here trying to catch some raw eggs without breaking. So to do that, we say you need soft hands, like catching a hard cricket ball. Because soft hands mean that your hands move as you're catching the cricket ball or the egg, increasing the time it takes for that egg to come to a stationary position. Smaller force. Smaller force means you've got less chance of breaking the egg. And then the last one, an engineer setting up a crash test dummy ready for deceleration and force data collection. And that's here. What have you got to do in the next page? I'll give you a moment just to read through that. Just pause the video. What you've got to do is answer these questions on page 27. And the idea being is that you then will work out the forces that act on the crash test dummy in experiment 1 and experiment 2, being experiment 1 when there's no seatbelt, experiment 2 where there is a seatbelt. So we'd imagine that the force acting on the crash test dummy in experiment 2 is going to be less than experiment 1. Now, in order to help you to do that, I'll do the experiment 1 part for question 1, 2 and 3, and you can do the experiment 2 part. So I'm just going to asterisk what you need to do, and I'll do experiment 1 on the left hand side, and then you can make that comparison at the end. So the first thing it's asking you to do is to draw on the graph lines for experiment 1 and 2. I'll do 1, you do 2. Lay them up as no seatbelt and seatbelt fitted. What do we know about experiment 1? I'm just going to highlight that. In experiment 1, the first experiment, it has no seatbelt on and hits the windscreen and decelerates from 0 to 0 meters per second in 0.4 seconds. So what I'm going to do here is get my ruler. 0.4 seconds. Let's zoom in a little. Here's here. Let's change my pen. Okay, I'll use a green pen. So that's 0.4. So we go up 0.2, 0.4, 0.6, 0.8 and 1. We can just about see at the bottom of the screen that the initial velocity was 26. So we've got 22, 24, 26. Get your ruler. And draw in the velocity time graph for experiment 1. Let's try that again. Better. And it does ask you to label each line. So I'm just going to label that EX1. So that's the first part of question 1. What you're going to do now is do the same line for experiment 2, where it's not taking 0.4 seconds, it's taking 2.5 seconds. I'll leave that for you to do. And then moving up back on to page 27, it says calculate the rate of deceleration with each experiment. So you use the equation for acceleration, change in velocity over time taken I should say. The change is 26 and the time taken is 0.4. 26 divided by 0.4, 65. So just write that answer in. 65. It's a huge deceleration. By the way, it's a deceleration, so I should have negative in there because the speed is getting less. Meters per second squared. Watch the units again for acceleration. Many pupils forget or mix up these units with the unit for speed or velocity. You do the same now for experiment 2. Then underneath it's asking what's the force acting on the crash test dummy. We'd imagine it's going to be quite a large force because of the large acceleration. We use this equation, Newton's second law. We need to know the mass of the crash test dummy. We know the deceleration is 65 or minus 65, doesn't matter. We just want to work out the magnitude of the force, the size of the force. In terms of, going back to that, yeah, force is a vector, so what we're saying is the person's moving that way to the right hand side, so we take that as a positive direction. The force is going to be acting that way in a negative direction, so that's why we would get a negative answer for force. Right, we need to work out then, or not work out, find out then it is, the mass of the crash test dummy, 70. Therefore we need to multiply 70 by 65. 70 multiplied by 65, that gives us 4,550. I've just written the answer down there, 4,550. So you'd imagine the answer you get here for experiment 2 would be a lot less. Pause the video and complete. Moving on to the last activity, which is at the bottom of page 27, all of 28 and the top of page 29. It's a literacy activity where you need to read, highlight and synthesize the information into this activity. There's a red asterisk there just to identify it's for you to do. What you need to do then is explain how these different safety features work. Crumple zones, impact bars, airbags and seat belts all use the following physics principles to keep vehicle users alive. Excuse me. Let's look at the first one, crumple zones, and I'll leave you do the rest. So we'll go back up. Crumple zones, there's some information here. So you read that paragraph and it's asking for what's the science, the physics behind how they work. Explain how they work. So you can say, look, if I read in here, there's one at the front and one at the rear of the car. That doesn't tell us how it works. It's describing, it's not explaining. The front crumple zone allows the bonnet of the engine to concertina upon itself as it's gradually pushed back into the car along extremely stiff rails. Here we go. This increases, so I would say the crumple zone allows the engine to concertina upon itself. This increases the collision time and also takes a great deal of kinetic energy out of the crash. So you'd use that information highlighted there, and you'd synthesize it, you'd put it in your own words here, and then you do the same for impact bars, airbags and seat belts. If you find that there's not enough information there for you, you can always research it on the internet. Well, that brings us to the end of lesson 4, and actually it brings us to the end of and the completion of all the content for this topic on work and energy. The remaining pages are exam questions where we'll look at those in a separate lesson. Make sure, please, you do the written 6-mark question, written assessment, and it's looking at the quality of your written communication. So as well as explaining how safety features work, you also get marks for your spelling, punctuation and grammar. See you next time. Bye.